Oh, class. Okay, so we're going to talk about something called diffraction. Now, let's say that we have a source of plane waves moving to the right. So this whole thing is moving to the right. These are sound waves. They're moving at the speed of sound. And let's say we hit a barrier. Well, we hit a barrier that, like a partial barrier. It's going to block part of the wave. Now, we can represent waves in two ways. One is with wave fronts, the other is with rays. Well, let's look at like this wavefront approach. So like this wavefront's moving along, and then what is going to happen when you look out, you look past this barrier, like this wavefront hits it, it looks like everything above here and everything below here, here is going to get cut off, and so you might expect something like this. The wavefronts that pass through are going to be just confined to this area. But this is not what you would actually see, or in the case of sound waves here, this isn't what happens when waves cross through a barrier. What happens is actually a bit more complicated. Similarly, you can look at with rays, and if you have a ray, going through the middle, you think it's going to pass through. If you have a ray nearing the top, it'll pass through. But then we'd get a similar picture just looking at rays. But again, this is not what happens. What happens is when these waves pass through this barrier, they do start out like this because they have to. But then when they move outwards, they spread out. And this is a fundamental property of waves that you don't see with like particle behavior too much. Like if you were just to have like a stream of particles hitting this, they'd follow a pattern like this. Everything that was going, it doesn't hit the barrier, it's just going to keep moving in a straight line. But then everything that hits the barrier is going to stop. So you just get like a beam of particles moving like this in that region between those two dashed lines. But waves spread out when they pass through a barrier. And when it comes to light, there was a dispute that lasted for hundreds of years about whether light behaved more like a particle or a wave. And Isaac Newton seemed to favor this particle approach. He wrote a book on optics. I tried to read it. It is virtually impossible to read this thing. Not because the physics is so complicated or the math. It's just, if you look back at old writing, they don't write like we do, and it's very hard to make sense of what he's saying. But a really interesting book, anyways. I'm trying to read it, but it's hard to make sense of some of it. But he seemed to favor this particle approach. And because, Isaac Newton was Isaac Newton, one of the greatest physicists of all time, that was a very influential approach that lasted for a very long time. And Newton actually was able to, this book he wrote on light was extremely important. It's kind of a collection of everything known. He designed all these really impressive experiments and discovered a lot of things. Now, his approach by saying light is a particle isn't exactly right. And I think it was the 1800s, I think I mentioned before in class, Thomas Young. He designed an experiment that showed light had properties like this, where waves, we get very different, like particles would behave like these dashed lines, waves do this, where they spread out. And he showed that light actually does that. So there is some pretty compelling evidence that light should behave like a wave. But it wasn't conclusive, and the debate continued until the late 1800s. basically the work of two people. Well, more than that, but there's the fundamental theoretical insight was due to a guy named Maxwell, who discovered that light can be seen as an electromagnetic wave. So obviously a wave gives it away. Maxwell said that light is a wave. He made this discovery. Basically what Maxwell did is he discovered this concept of an electromagnetic wave. He had no idea what it actually was, but he was able to calculate the speed of this wave, that this electromagnetic wave would have to travel. And when he did the calculation, he found it travels at the speed of light. So he concluded light is an electromagnetic wave. And shortly after, a guy named Henrik Hertz, again, we named the unit Hertz, cycles per second, he was able to experimentally create electromagnetic waves and detect them. And so then this was settled once and for all. Light is a wave. There was zero doubt at this point. Or maybe very little doubt. But that picture didn't last long, because just a few years after that, Einstein came along and said, actually, light is both a particle and a wave. It actually has properties of both. But, yeah, I think getting a little off topic here. But yeah, particles and waves behave very differently in some cases. And sound waves or light waves both would have this property where they spread out. So interesting, like if you have a laser, you think of it as like a narrow beam of light. If you shine that through an opening, it's going to spread out. You wouldn't expect that from particle-like behavior, but that's what light does. It definitely has wave-like properties. Okay. Now, how do we explain the spreading out? And there's something called Huygens principle, where Huygens came up with this idea. Let's look at this plane wave. And what Huygens said is, let's consider this as a bunch of point sources that create spherical waves that spread out. So there's a little sphere attached to each of these particles. So like every point on the wavefront creates a plane wave. Now you might be thinking there's an infinite number of points. Yes, there are. So Huygens' principle in practice is very complicated to use. And it's not 100% correct, but essentially it captures what we're looking for here. And so we can apply our principles of interference. Like, say we have an observer at some location. What are they going to see? Well, let's just add up. We'll consider each point of this wavefront to be a source of spherical waves and add them all up, and that'll give us, just by using interference, we can tell what we're going to see at a particular location. And again, because there's an infinite number of points, this is a very complicated process. Definitely requires calculus. And it's not 100% correct, but it contains the essential idea. And what Huygens was able to show is that a plane wave is going to create, like the next wavefront is going to be another plane wave. And then this wavefront, this wavefront will create the next one, which is here. And so, as long as there's nothing blocking the wave, if we have like an infinite plane wave, that's going to create another infinite plane wave, and so on. But then when we get to the barrier, we have to consider a situation like this. I'll just erase this picture and start over. Here's our barrier. And now, like say, this is our wavefront here. And let's say this barrier, it's like a rectangular barrier, and it has a width W. And let's say we have a screen here. And we want to know, like, what like at any given location, let's draw like on right down the middle of the width. Let's say this is y equals 0. And what are we going to get at y equals 0? And then, like as we go away from the center, what are we going to see? And I'm going to plot the pattern actually off to the side. This is what we're going to actually see. So let's say that this is our barrier, all of it from a different perspective. And we're shining light onto a screen. If we plot the intensity of the light, it's going to be very bright directly across. We're going to get a pattern that looks something like this. It's kind of an interesting looking pattern. Where like directly across from the screen, this graph is very tall. We're going to get a lot of light in this region directly across from the screen. But then as we move away from the screen, so again, like this point here would be y equals 0. As we move away from the screen, the maximum intensity is going to occur right in the middle. And as you move away from that, eventually at some point, let's say right here, the intensity is going to go to 0. But then if you move past this point, the intensity is going to rise again. And so what's going on here, and again, it's this complicated interference because we have to consider every point on this wavefront as a source of spherical waves and then add up that infinite number. Very complicated process. So what we're going to do, let's just look at that point D. That point where we move away from the first place we get destructive interference. That's point D. And basically, let's look at, let's draw like this triangle here. Now again, this is just a two-dimensional picture. What we'd actually be looking at is like a cone coming from this opening. And we can see that most of the energy is directed in this cone that's defined, but like there's another D on the other side. Another point where we get destructive interference. So the light spreads out, but most of it is directed along this cone. Again, it looks like just like a triangle, but it's going in all directions. I think I might have a picture. Yeah, not a great picture, but just from an example in the notes. Try to draw more of a three-dimensional picture. You can see these cones here. And let's define this angle to be theta. The angle from y equals 0 to that first place we get destructive. Okay, so we have this cone where all this energy is directed, or most of the energy. What's going on here is interesting, but not all that significant as far as energy is concerned. And so we want to find this angle theta. So how are we going to do that? We're going to use Huygens principle. So what we're going to do is we're going to look at and draw these two. Let me erase this in the middle. So we're going to draw lines from the like the top point and the bottom point to D. And this is the path length difference between the two. So like these two distances are the same. And delta is a path length difference. And because we have destructive interference here, I'm going to say delta equals lambda. Now, if you've been paying attention, you might think I just made a mistake. Delta equals half a wavelength should give us destructive interference. But now I'm saying delta equals lambda gives us destructive interference. And the reason why we can't use this formula, because that formula, we just had two sources meeting at a particular location, where here we have an infinite number of sources. Every point on that wavefront, we have to add them all up. But I think I can make an argument that, hopefully convincing, that delta equals lambda gives us the right answer. So this point right here is the midpoint. And let's just say that delta equals lambda. Let's just go with that. Now, because this is the midpoint, if this is lambda, we have a triangle here. So if we cut it in half, like this angle's the same for both triangles. And so this distance, we cut this side in half, similar triangles. If this is lambda, this is going to be 1/2 lambda. So what we can say is, just looking at this source, this point here, and this point here, these two are going to be exactly out of phase and interfere destructively. Okay? So this ray and that one interfere destructively. Now, if we look at a point just beneath each of these, the path length difference between these two is also, this point is a certain distance below the top point, and this one is that same distance below the midpoint. They're going to also be out of phase. And so, just by adding up all the contribution from all these waves, these two cancel out. Beneath, every point here is canceled out by a corresponding point beneath the midpoint, the same distance. So if we add them all up, they're all going to cancel out. You can break it up into as many pieces as you want. Let's say we break it up into 5 pieces. Picture is not that great anymore, but so this point and this point cancel each other out. And then this point and this point are going to cancel each other out. And every point, there's a point directly above the center and one directly above this bottom end point that cancels out. Basically, every point above has a point below that will cancel it out. And so delta equals lambda is the right distance, path length difference, to get all these waves to interfere destructively at that point. Okay, now we want to find this angle theta. So we define theta to be this angle. And I'm going to start over. Draw the same picture, just a little less cluttered. So here's our screen. Actually, I don't need that line, so I'm not going to draw it. So this angle's theta. We also have so I'm going to draw these as if they're parallel. And again, we're assuming that this screen is far enough away that these lines can be considered parallel. Obviously, if they're parallel, they never meet up. But if there's even a small angle between them, if you go far enough, they'll meet up. So if the screen is far enough, they're effectively parallel. But for our purposes, we're going to basically say that this angle's theta and this angle's theta as well. So, and then we drew this line here and said that this distance is lambda. That was our initial wavefront. And so if this angle's theta, this angle is going to be 90 minus theta, which makes that angle theta. Remember we said W is the width of the opening. And so we have this right triangle here. I mean, that's a right angle. I don't want to draw it inside because that clutters it up. So again, putting it on the other side is just as good. And so we can see from this triangle that sine of theta is lambda over W. And so that's the diffraction angle. So when you have like a rectangular opening like we have here, like, you know, this barrier is perpendicular to the screen, and it extends far enough that we don't have to worry about the edges of it. So we just have this opening, and again, this opening extends along the length as well. So you can almost think of this like a doorway. Like here's the walls on each side, here's a doorway. And so again, you have these waves going through. And again, they're going to spread out in this cone defined by this angle, theta. And we can say that, you know, sine of theta is lambda over W. That's where most of the energy is directed. Okay. Now that's just a rectangular opening. There's another example, and it's something we're definitely not going to try to derive, but it's a very important example, and this is for a rectangle that we have here. Now, what if we have a circular opening? So we have a wave passing through a circular opening, and let's say this opening has a diameter d. So this, like say that this whole screen is filled in, but I cut a hole in this board here, and we have wave fronts, like plane waves moving this way. They're going to spread out, and they're going to form a cone just like before. The details will just be a little different. And I'm going to write down the result. It's 1.22 lambda over d. Now, this is a very important result because things tend to pass through circles. Like if you have speakers, you know, those are circular. And again, particularly if you go to the subject of optics, if you look at light instead of sound, every time you're seeing light, it's passing through a circular opening. That'd be the pupil of your eye. And so this one is extremely important. Like, more so for light because, yeah, like instruments, like microscopes, telescopes, yeah, obviously your eye. All of these, you know, they tend to be circular openings that the wave has to pass through. And so, very important example, the circular case. Okay, so that's diffraction. And one thing, what if we have an extremely high frequency wave? So remember, higher the frequency, the smaller the wavelength. What if we have a very high frequency, so the wavelength is 1 millimeter? It'd be easy to calculate the frequency we would need. Just be the speed of sound divided by the wavelength. This would be very high frequency. Well, let's say we did that. And let's say we sent it through, let's say a circle with a diameter of 1 meter. What angle would this cone be? Well, we'd have sine of theta would be 1.22 times a millimeter. The diameter is 1,000 millimeters. So we'd have sine of theta is about 0.00122, which means theta is going to be around 0. We're not going to really get much diffraction. The sound is not going to spread out too much if it's going through this large opening. And it's relative. You know, a meter, normal sound waves, if you have, say, a frequency of 343 hertz, the wavelength would be a meter. And so, typically, sound waves that we hear are higher than that. Like you could have, say, a 500 hertz wave. The wavelength would be a little less than a meter. And so, yeah, it's a relative thing. But, yeah, with a wavelength of 1 meter, this is a huge opening, and you're not going to notice much diffraction. That's why, like, if you have a laser beam and you shine it out a window, you're not going to notice the beam spreading out, although it has to, but it's going to be an unnoticeable amount. Diffraction is significant when the wavelength of the wave is comparable to the size of the opening it's passing through, either the diameter or the width. That's when diffraction becomes significant. If the wavelength is much smaller, it's not going to be nearly as significant. Okay, so yeah, I think that's it for diffraction. We have one more topic to talk about here, but I think I'll do that in a separate video to keep this length reasonable. And that other topic is something called beats. And after that, there's only one more section that we're going to cover in the class. We're getting near the end. So yeah, diffraction, just think waves when they pass through an opening, they spread out. And when the wavelength is comparable to the size of the opening, that's when diffraction is significant. So I think that'll be it for this video.